Tonight, let's do something gentle and a little playful. Not a chase, not a puzzle you have to solve, just a slow, quiet walk through a gallery of worlds. Because 2025 has been a year where exoplanets, planets beyond our solar system, have started to feel less like distant points on a spreadsheet and more like places with texture. We are not traveling there. We are not landing. We are not hearing alien winds with our own ears, but we are beginning to sense shape, motion, heat, chemistry, and time in a way that is surprisingly intimate considering these worlds are light years away. So think of this episode as a sleep-friendly tour. Each stop will be strange in its own calm way. Some of these worlds are strange because of where they live, in systems that seem, at first glance, almost impossible. Some are strange because they are changing right now, losing their atmospheres, shedding their surfaces, leaving trails behind them. Some are strange because they challenge the simple ideas we used to carry, that small rocky planets must be airless if they are too hot, or that planets should form in neat planes, or that a planet is always a simple, round thing. And through all of them, there is a quiet, steady truth. The universe is very good at making exceptions. Before we begin, let's set a small foundation so the strangeness has context. For most of human history, planets were a local concept. We looked at the wandering lights, Mercury, Venus, Mars, Jupiter, Saturn, and we slowly learned they were worlds. Then we found Uranus and Neptune, and later, in the cold edge, Pluto. Even then, all the planets we knew belonged to one star. Exoplanets changed that. They told us that planets are not rare ornaments, they are a basic output of star formation. And as the count grew into the thousands, a pattern emerged. Nature does not build by copying a single template. Nature explores the whole menu of what physics allows. What does that mean practically? It means there are planets that are puffier than you would expect, planets that are denser than you would expect, planets that orbit in hours, planets that orbit two stars, planets that may have oceans under thick atmospheres, planets with skies full of metals and soot, planets that are being pulled apart right now. The strangest part is that none of this requires fantasy. It is simply gravity, radiation, chemistry, and time running in different combinations. If you are listening while trying to sleep, you do not need to remember names. You can let them drift by like the names of distant islands. What matters is the feeling. The universe is broad, and it is busy, and it is oddly creative. One more grounding idea. When astronomers say they discover an exoplanet, they often mean something subtle. Most exoplanets are not photographed as little disks, they are inferred. A star dims slightly and regularly, a transit. A star wobbles, a radial velocity signal. A disk of dust shows a gap, a possible shepherding planet. A background star brightens, microlensing. These are careful measurements, not dramatic images, which is why the phrase strange exoplanet doesn't mean definitely weird. It means we have evidence that something unusual is happening, and the simplest explanation is a planet. And sometimes, with better instruments, we move from inference to detail. We can begin to measure an atmosphere. We can see heat moving from day side to night side. We can detect gas escaping into space. We can spot a young planet glowing in infrared, still warm from birth. That is the spirit of 2025. More detail, more texture, more ways for a world to surprise us. So, here's how we'll travel. We'll start with worlds that challenge the geometry of how planets should orbit. Then we'll visit a baby world being born in a dusty ring. Then we'll meet worlds that are actively losing themselves, leaving tails behind them. Then we'll pause on an extreme rocky planet that might hold an atmosphere when it shouldn't. Then we'll end with one of the strangest environments of all, a planet associated with a pulsar, and reflect on what it means that nature can still find a way. If you are still awake, you can treat this as a question to hold loosely. When you imagine a planet, what do you picture? A sphere? Surely. A stable orbit around a normal star? Surely. A climate that changes slowly. A sky that, even if it is strange, is still made of familiar molecules. Now notice how gently those assumptions begin to loosen. And if you want to share your own image of a planet, your default mental picture, tell me what it looks like in your mind. What do you think of first? Comment below. Now, let's begin with a world that seems to orbit in the wrong direction. Not backwards exactly, but sideways. A planet that appears to circle over the poles of two dim, failed stars. Our first stop is a system that feels like a quiet rebellion against neat diagrams. It is informally known as 2M1510. And what makes it memorable is not only that it has two suns, but that its orbit seems to be tilted into a rare configuration. Most planetary systems, including our own, are fairly flat. They form from a rotating disk of gas and dust. Planets condense inside that disk, and they inherit its plane. So you can draw it as a dinner plate. The star is the center, and the planets are beads moving around on the plate. But in 2025, researchers highlighted a candidate planet in the 2M1510 system that appears to be on a polar orbit, tracing a path that carries it far over the poles of two brown dwarfs. Brown dwarfs are sometimes called failed stars. They are too massive to be planets, not massive enough to sustain hydrogen fusion like a true star. They glow dimly, especially in infrared, and they live in a middle category that feels itself like a reminder that nature loves gradients more than boxes. In this system, two brown dwarfs orbit one another, and the proposed planet does not seem to follow their shared plane. Instead, it takes an orbit that is almost perpendicular. This matters for a simple reason. It suggests that the disk that formed the planet, or the dynamics that shaped its orbit later, were more complex than the usual story.
How could that happen? One possibility is that the disk was warped, twisted by gravity, by an additional companion, or by interactions that nudged it out of alignment. Another is that the planet formed in a more typical plane and was later torqued into a polar orientation through long-term gravitational exchanges. The details are still being refined. The big idea is that the universe is willing to place planets in places that look, to our eyes, like unstable choreography. And yet, they persist. If you let your imagination drift, picture it like this. Two dim, reddish-brown objects circle each other in a slow, steady dance. Between them, space is not empty, it is alive with gravity. A planet, unseen directly, inferred by the subtle shifts in the system's motion, loops around them on a path that rises and falls like a ribbon lifted off the plate. If you were standing on that planet, and if the sky were bright enough to call it a day, you might see the two suns tracing arcs that do not match the familiar ecliptic. The geometry of sunrise and sunset could feel unfamiliar, like seasons drawn with a different compass. This kind of system is useful in a practical way too. The fact that we can infer such a configuration means our instruments and methods are sensitive enough to notice geometry, not just presence. It is a hint of where exoplanet science is going, from counting planets to mapping their architecture. And if you want a quiet thought to hold, how much of what we call normal is simply what we have seen most often? Because once you find one polar orbit planet, you begin to wonder how many more exist, hidden in the noise of observations, waiting for a longer data set or a slightly better model. In 2025, systems like this also carried an emotional lesson. They remind us that planetary formation is not a single story. It is a family of stories. Some are tidy, some are not. Now let's move from strange geometry to strange youth, because another kind of exoplanet strangeness is not about how a planet ends up arranged, but about catching it in the act of becoming. For most mature planets, we see the finished sculpture. The disk is gone, the planet is quiet in its orbit. But in rare cases, we see a system that still looks like a workshop. A bright star, rings of dust, and a small object glowing within a gap. And in 2025, a baby planet named Wispit 2b offered one of the clearest views yet of that workshop. Imagine a ringed disk like a cosmic vinyl record, pale and thin, circling a young star. Within that ring, a gap opens, a clearing that hints at a sculptor. And inside that clearing, a faint point appears. That point is the candidate planet, still hot, still bright from formation, still embedded in the leftovers of its birth. It is the kind of observation that turns an idea into a scene. Because for decades, astronomers suspected that gaps in disks were carved by planets. But suspicion is not the same as seeing. To see a forming planet within the gap is to watch gravity doing its slow work. A planet sweeps material, shepherds dust, and gathers gas. The disk responds. The structure changes. If you pause on that image, you can sense time. Not time as minutes or hours, time as millions of years. A star only a few million years old. A planet still accreting. A system that looks like our own solar system might have looked like when the Earth was not yet a concept, only a possibility. There is also a quiet humility in this. We tend to imagine planet formation as a clean process. Dust becomes rocks. Rocks become planets, planets become stable. But these images show a messier truth. Rings, gaps, clumps, collisions, spirals, and long settling. The end product may look orderly, the process is not. And that brings us to another kind of strangeness. Not a strange orbit, not a strange birth, but a strange fate. Because in 2025, the exoplanet story is full of tales. Not tales like animals, tales like comets. Long trails of material streaming away from worlds that are too close to their stars. So, let's drift onward, from the workshop of birth to the slow unraveling of a planet that is, quite literally, leaving itself behind.
The exoplanet we visit next is not just strange, it is temporary. There is something quietly haunting about that. We are used to thinking of planets as stable anchors, long-lived, patient, indifferent. But some planets are caught in a brief chapter where the star's heat is actively pulling them apart. In 2025, one of the most vivid examples was a small world called BD plus 054868 Abe, observed by TESS. This planet orbits so close to its star that its year is barely more than a day. At that distance, the surface is not simply hot, it is hot enough that material can vaporize and escape. And as that material escapes, it can condense into dust, and that dust can form a tail. A planet with a comet-like tail. When astronomers see this, they are not only seeing a dramatic silhouette, they are seeing a new kind of planetary science, the chance to sample a planet's interior indirectly. Because if the tail contains dust from the crust, or the mantle, or even deeper material, then the light that filters through it could reveal what the planet is made of. In our solar system, we study interiors with seismic waves, with meteorites, with samples. Across light years, that is not possible. But a disintegrating planet is, in a sense, doing the sampling for us. It is shedding itself into space. This is why the strangest exoplanets are not only curiosities, they are opportunities. Still, let's keep the tone calm. There is no need for drama. Picture it gently. A small, rocky body, tidally locked, one side always facing the star. The day side is a furnace, the night side is cooler, but still warm. Between them, the terminator line, the edge between day and night, is a place of sharp gradients. From the day side, vaporized rock escapes. Particles and gas stream away. Starlight pushes the dust, shaping it into a trailing arc. And when the planet passes in front of its star, the transit light curve is not symmetrical. It dims in a way that suggests a head and a tail. That asymmetry is how the story becomes visible. If you want a quiet question, what would it mean, emotionally, to live in a system where the very existence of your world is slowly evaporating? Not in an apocalyptic week, but over 1,000,000 years, slow enough that no single generation would notice, and yet real enough that on cosmic timescales, it is a brief and fragile phase. The tale reminds us that planet is not always a final state. Sometimes it is a phase between disk and dust, between formation and dispersal. Now, there is another kind of tail, not dust from rock, but gas from an atmosphere. Because in 2025, JWST showed us something beautiful and subtle. A giant planet losing not its surface, but its sky. Consider an ultra-hot Jupiter, a giant gas planet orbiting so close to its star that its atmosphere is heated to thousands of degrees. At those temperatures, light gases can escape. The planet becomes a source of its own outflow. This is a different kind of disintegration, not a crumbling rock, but an atmospheric leak. And one of the most striking cases this year involved WASP-121b, also known by its mythic nickname, Tylos. JWST observations revealed that this planet is surrounded by immense helium tails. Not one tail, but two. A trailing tail pushed back by the star's radiation and wind, and a rarer leading tail that curves ahead, likely shaped by gravity.
If you let that image settle in, it's surprisingly elegant. A planet is not only an object, it is also a source, a flow. Atmospheres are not static blankets, they are dynamic systems. They expand, cool, heat, escape, and respond to stellar forces. So in deep space, around a star, you can have a planet with a double ribbon of helium arcing along its orbit like pale, invisible silk. We cannot see it with our eyes, but the instruments can detect its signature. The strange part is not only that the tails exist, it is that we are now sensitive enough to map the structure of escape. That means exoplanet science is becoming less like a catalog and more like meteorology. Not whether you can feel, but whether you can infer. Winds, heat transport, chemical layers, and flows that shape a planet's fate.
Because it forces us to ask, what kinds of atmospheres can survive under starfire? Perhaps the atmosphere is not like Earth's. Perhaps it is composed of heavier molecules, or vaporized rock, or a mix of gases produced by constant outgassing from the interior. Perhaps it is replenished faster than it is lost. Perhaps the star is quieter than expected. Perhaps the planet's magnetic environment helps. Or perhaps our assumptions about atmospheric loss at these extremes have been too simple. There is a larger lesson here. The universe is not obligated to conform to our intuitive categories. Habitable and uninhabitable are not binary states. Atmosphere and no atmosphere are not always stable categories. A planet can be in between, thin, variable, replenished, transformed. Now, if you're listening for sleep, you can let the scientific details soften. Hold the image, a world close to its star. Half of it glows with heat. The other half sits in permanent darkness. Between them, winds may rush, trying to equalize a difference that is never fully resolved. And the atmosphere, if it exists, becomes the planet's quiet attempt at balance. This is where exoplanets become emotionally resonant in a calm way. They are not stories with characters. They are stories with gradients, heat versus cold, day versus night, gravity versus escape, formation versus erosion, and the most interesting worlds live in the tension. This is also where the instruments matter. JWST does not see a planet's atmosphere the way you see clouds. It senses tiny changes in starlight as the planet transits. It reads spectral fingerprints, the way certain molecules absorb specific wavelengths. And in doing that, it turns an exoplanet from a dot into a place with chemistry. Sometimes it even turns it into a debate. Because as we push instruments to their limits, interpretation becomes careful. This year, one of the most public exoplanet debates involved a world called K2-18b. This is not necessarily the strangest world physically, but it is strange in how it sits at the boundary of what we want to know. K2-18b is a sub-Neptune, a class of planet we do not have in our own solar system. It is larger than Earth, smaller than Neptune, and likely has a thick atmosphere. Some hypotheses suggest such planets could be Hycean worlds, ocean-covered planets with hydrogen-rich atmospheres, though that remains a concept to be tested, not a settled label. In 2025, K2-18b became a focus because of claims and counterclaims about chemical signatures in its atmosphere. One group argued that the spectral data hinted at molecules that, on Earth, can be associated with biology.
Other researchers responded that non-biological processes could reproduce similar features, and that the signal might be too noisy to support strong conclusions. And that back and forth is, in its own way, a kind of strangeness. Not the strangeness of a tail or a polar orbit, the strangeness of how close we are to the edge of inference. It reminds us that exoplanet atmospheres are not easy. The starlight is faint. The transit signals are tiny. The star itself can be active. Instrument systematics matter. So the right posture is not certainty, it is patience. And yet, even in debate, there is progress. We learn what is measurable. We learn which claims require more data. We learn how to build better methods. If you want a gentle question to place here, when you hear possible sign of life, what happens inside you? Does your mind rush ahead? Does it become skeptical? Does it feel excited or cautious or both? There is no right answer, but it is worth noticing because exoplanet science will increasingly invite that emotional reflex, and it will increasingly require discipline to match it. Now, we have visited a sideways orbit, a baby planet in a ring, a rocky planet that might hold an atmosphere when it shouldn't, a debate about chemistry on a distant world. Next, we can widen the lens. Some of the strangest exoplanet stories of 2025 were not about a single planet's surface or sky, but how our instruments are reshaping what nearby means. The closest star system to the Sun is Proxima Centauri, and in 2025, astronomers sharpened their view of its planets with a new instrument designed for precision. Let's drift there next, to the nearest neighboring star and the quiet challenge of measuring small worlds in infrared light.
Proxima Centauri is only about 4.2 light-years away. That is close in cosmic terms, still far beyond any human travel, but close enough that it often becomes a symbol. If there is a nearby rocky planet that might resemble Earth in some abstract way, we want to know. If there is a nearby system where we can test our instruments and refine our methods, we want to measure it. In 2025, the Near Infrared Planet Searcher, NIRPS, delivered results that helped confirm and refine the known planets in the Proxima system. Why does near infrared matter? Because red dwarf stars emit much of their light in infrared wavelengths. If you want to measure subtle signals around such stars, it helps to use instruments tuned to the star's natural glow. NIRPS, working alongside other data, helped confirm the presence of Proxima b and Proxima d and refine their parameters. This is not a strange planet story in the sense of a tail or a polar orbit. It is strange in another sense. It is a reminder that our view of the universe depends on engineering choices. A new instrument can transform an old question. It can confirm what was uncertain. It can rule out what was suspected. It can reduce noise, tighten constraints, and sharpen the outline of reality. So, in the calm rhythm of this episode, Proxima's contribution is this: even the nearest planets can remain uncertain until the right tools arrive. And that too is part of the exoplanet era. We are not only discovering worlds, we are building the senses needed to study them. Now, after this pause, we can return to the more overtly strange, because there is one category of exoplanet that feels like it belongs to science fiction, and yet it is firmly within physics. Planets around dead stars. When a star like the Sun dies, it does not explode as a supernova. It expands into a red giant. It sheds its outer layers. It leaves behind a white dwarf, a dense, hot remnant.
White dwarfs can have debris disks. They can accrete fragments of asteroids or planets. They can carry chemical traces of destroyed worlds. In 2025, the broader exoplanet narrative included glimpses of destruction around such remnants, evidence that planetary systems can survive a star's death, but not always peacefully. When the star changes, gravitational relationships shift, orbits destabilize, objects collide, fragments spiral inward. This is a quiet version of chaos, and in its shadow there is another kind of dead star, the pulsar. A pulsar is not a gentle remnant, it is the collapsed core of a massive star that did explode as a supernova. It is a neutron star, extremely dense, rapidly spinning, and often intense in its radiation. A planet around a pulsar seems, at first, unlikely. The supernova that creates the neutron star is violent. It should disrupt or destroy nearby planets. And yet, planets have been found around pulsars. Some of the earliest exoplanet detections were in such systems. But in 2025, JWST gave us a new kind of pulsar planet story. Not merely the detection, but a surprising look at the planet's atmosphere. This is where the tour becomes truly strange, not in a loud way, but in a quiet, almost surreal way. Because the planet, named PSR J2322-2650b, appears to have an exotic atmosphere dominated by helium and carbon, with soot clouds and the possibility that deep within, carbon might condense into diamond under immense pressure. A planet with soot in its sky, a planet that might rain carbon into gemstones. Even if you treat this cautiously, even if you remember that atmospheric retrievals are complex, the result is still remarkable. We can detect unusual atmospheric composition on a world associated with a pulsar. That fact alone says something about the power of our tools and the variety of nature. We will spend the final portion of this episode on that world, what it might be, why it is perplexing, and how it expands the boundaries of planet formation stories. But before we do, let's take one last detour through a theme that has been quietly growing in 2025: direct imaging. Most exoplanets are found indirectly, but sometimes we can actually photograph a planet as a faint point of light next to its star, especially if the planet is young and still warm. In 2025, Webb captured compelling evidence for a lightweight planet around a young nearby star named TWA7. If confirmed, it would represent one of Webb's first direct image planet finds and one of the lightest planets ever seen with that technique. The planet is referred to as TWA7b. It sits within a debris disk, a structure of dust and small bodies. In images, the disk appears like a delicate set of rings, and the planet appears as a faint glowing point near one of the ring gaps. This is strange, not because the planet itself is inherently exotic, though youth is always interesting, but because it marks a shift. We are beginning to see planets as objects, not only as effects, a point of light, a presence, a thing. And that shifts the emotional weight of exoplanets. It makes them feel less abstract. So, as we approach the end of the episode, we carry with us these threads: odd geometry, planet birth, planet loss, unexpected atmospheres, instrument breakthroughs, direct imaging.
Now we can gather them around the strangest environment of all. A planet near a pulsar with a chemistry that seems to defy our expectations. Let's go there. To approach a pulsar planet calmly, we should start with the star itself.
A pulsar is, in a sense, a lighthouse made of matter at nuclear density. A massive star ends its life in a supernova. The core collapses until protons and electrons combine into neutrons. What remains is a neutron star, a city-sized object with more mass than the Sun, spinning rapidly. Some neutron stars emit beams of radiation from their magnetic poles. As they spin, the beams sweep across space. When the beam crosses Earth, we detect a pulse. Pulse after pulse, precise like a clock. This is why pulsars were once used as the most stable timekeepers in the universe. Now imagine trying to host a planet in such an environment. The birth of the neutron star was violent. The radiation can be intense. The gravitational field is extreme. So how could a planet exist there? There are a few broad possibilities. One is survival. A planet forms before the supernova and somehow remains bound afterward. This is difficult but not impossible, depending on distances and how much mass is lost in the explosion. Another is second-generation formation. After the supernova, a disk of material forms around the pulsar and planets form out of that debris. This is an exotic path, but it offers a way to create planets after a star's death. Another is capture. The planet might be a remnant of a disrupted companion, reshaped by tidal forces. Each of these scenarios carries uncertainties, and that is part of why pulsar planets remain puzzling. Now, in 2025, JWST observed PSR J2322-2650b and found its atmosphere to be unusual. Instead of the familiar set of molecules often discussed in exoplanet atmospheres, water vapor, methane, carbon dioxide, the atmosphere appears dominated by helium and carbon. On top of that, soot clouds are inferred, and deeper, under immense pressures, carbon might condense into diamond. Even if you keep your skepticism engaged, the result still invites wonder. How do you create an atmosphere like that? One possibility is that the planet's origin is not like typical gas giants. Perhaps it is a stripped remnant, or a world that has lost certain layers and retained others. Perhaps its chemistry reflects the unique environment of a pulsar system. Another possibility is that the atmosphere is shaped by extreme irradiation, breaking apart molecules and leaving behind a different chemical equilibrium. Under intense radiation, ordinary molecules can be destroyed, and the survivors can be the ones that are stable in that harsh regime. Another possibility is that the atmosphere is not primordial at all, not the original composition of a planet's birth, but the result of long-term alteration, escape, and replenishment. And then there is the question of clouds. Clouds in exoplanet atmospheres are often made of things that sound strange because we are used to Earth's water clouds. In hot Jupiter atmospheres, clouds can include silicates, iron, or other high-temperature condensates. On a carbon-rich world, soot-like particles can form. Carbon can polymerize, clump, and create hazes that absorb and scatter light. So soot clouds are not a poetic idea. They're a plausible physical outcome in certain chemical regimes. Now, here is where we can soften the story again, because the details can become dense. You do not have to hold every mechanism, just hold the scene. A planet, close enough to a pulsar that gravity can distort it, orbiting quickly. A sky not blue, not water-based, but darkened by carbon haze. Deep layers where carbon might crystallize under pressure. It's like a world from a dream,
but built out of chemistry and gravity. If you want a quiet question to place here, do you think the strangest planets are the ones that resemble nothing we know, or the ones that resemble something familiar but in an unfamiliar place? Because a planet with clouds is familiar, but clouds of soot near a pulsar is unfamiliar. Now, another reason this JWST result matters is methodological. JWST was designed for deep infrared observations. It can do many things, and exoplanet atmosphere measurements are among its most delicate tasks. But a pulsar is a complicated target. Pulsars can be intense in high-energy radiation, but JWST's infrared measurements can sometimes avoid the worst of that interference. So JWST is giving us a window into a place we might not have expected it to explore so effectively. And that is another theme of 2025. Instruments are being used in ways that expand their original purpose. Now, we should also acknowledge a calm scientific caution. Atmosphere retrievals, the process of inferring composition from spectra, involve models. Different assumptions can yield different interpretations. Clouds can mimic the signatures of certain molecules. Noise can create patterns that look meaningful. So the right posture is, this is a fascinating result, and it should be tested, repeated, and refined. But even that caution doesn't remove the beauty of the effort, because the effort itself is astonishing. We are reading the chemistry of a world around a dead star using a telescope that orbits our own. Now, to keep the episode sleep-friendly, we can gently step back from the specifics and ask a broader question. Why does the universe produce such extremes? The answer is not a single principle, it's the combination of many. Different stellar types, different disk conditions, different migration histories, different radiation environments, different ages. Over billions of years, the galaxy runs experiments again and again, and we are sampling the results. Now, in the last segment of our tour, we'll tie these worlds together. We'll ask what strange really means in science, and we'll end with a calm invitation to curiosity. Because the goal is not to collect weird facts. The goal is to feel, quietly, how large and varied reality can be. So let's move toward the closing. Let's gather the tails, the rings, the sideways orbit, the lava world, and the soot sky, and let them settle into one gentle conclusion.
When you step back, the strangest exoplanets of 2025 are not a random list. They fall into a few quiet themes. Theme 1. Architecture. The 2M1510 system reminds us that planetary systems can be arranged in ways that do not match the familiar plate-like picture. A polar orbit suggests warps, torques, and histories that add dimension to the flat diagrams. Theme 2. Origin. Wispit 2b, seen as a faint point embedded in a ring gap, reminds us that planet formation is not a clean, finished process. It is a messy workshop. The planet is still bright from birth, still sculpting the disk that birthed it. Theme 3. Loss. BD plus 054868A shows us a rocky world with a tail, a planet in the act of disintegrating, shedding material that may reveal its interior. WASP 121b shows us atmospheric loss, helium streaming away in enormous tails reshaped by radiation, wind, and gravity. Theme 4.
survival where we did not expect it. TOI 561b suggests that a rocky lava-hot planet might still hold atmosphere, redistributing heat in defiance of simple expectations. Theme 5. Environments we once considered nearly impossible. A planet associated with a pulsar with a helium and carbon atmosphere and soot clouds challenges our sense of where planets can exist and what they can be made of. And behind all those themes is a sixth: our instruments. NIRP's refining Proxima's planets, Webb imaging the lightweight candidate around TWA7, Webb reading the chemistry of atmospheres, watching tails, and mapping heat. In other words, 2025 is not only a year of strange planets, it is a year where our senses have improved, and so the universe appears stranger. Not because it changed, but because we can see more. That is an important lesson. Sometimes the world feels mysterious, not because reality is hiding, but because we have not yet built the right way to look. Now, there's a gentle philosophical twist in this. Strange is relative. A hot Jupiter would have seemed absurd in 1990. A planet orbiting every few days, larger than Jupiter, closer than Mercury, would have felt like a violation of the solar system template. Now, hot Jupiters are common. A sub-Neptune would have been strange too. Now we know they are abundant. So the strangeness of 2025 may become the normality of 2035. That does not diminish it, it completes it. Because what we call strange today becomes part of the expanded map of normal tomorrow. And that expansion matters, especially for the most delicate question of all: life. Not because every strange planet is a candidate for life, most are not, but because understanding extremes teaches us the boundaries. If a lava world can hold an atmosphere, we refine our models of atmospheric loss and retention. If a sub-Neptune's chemistry can mimic biological signals, we refine our models of false positives. If dust tails reveal interiors, we refine our understanding of rocky compositions. If polar orbits exist, we refine our understanding of disk dynamics. Knowledge is often built on exceptions. Now, if you are awake and you want to engage, here's a calm question. Which kind of exoplanet strangeness fascinates you most? Is it the geometry, planets in odd orbits and multi-star systems? Is it the process, baby planets in dusty rings? Is it the transformation, tails, escape, disintegration? Is it the chemistry, soot clouds, unusual atmospheres, hints and debates? There is no wrong answer. Your preference is a reflection of what kind of mystery your mind enjoys. Now, we can also acknowledge something important about the US and UK audience for a sleep-friendly cosmic documentary. People often want wonder, but they do not want anxiety. They want the feeling of the universe being vast and beautiful, not threatening. So we keep the tone gentle. Even when we describe extremes, we describe them as physics, not as danger. There is no need to fear a pulsar planet. It is far away. There is no need to fear a disintegrating world. It is a lesson in heat and gravity, not an omen. The universe contains violence, yes,
but it also contains stability, and the beauty is that both can exist in the same set of laws.
Now we are approaching the quiet end of the episode. To finish, we can do something simple. We can return to the starting image, the idea of a planet, and watch how it has changed. At the beginning, the default planet was likely an Earth-like sphere orbiting a Sun-like star, maybe with blue oceans, maybe with clouds. Now, after this tour, the word planet includes a world that orbits two brown dwarfs on a polar path, a newborn planet glowing in a disk gap, a rocky planet trailing a dust tail like a comet, a lava world that might still carry air, a planet with soot clouds around a pulsar. The concept is broader, and that broader concept is in itself calming, because it suggests reality is not narrow, reality is not brittle, reality is spacious. When you think of the future, you can imagine that the list will grow. More tails, more young worlds, more mapped atmospheres, more surprises. The strange will become familiar, and the familiar will continue to expand. In the final 3 files, we'll slow even further. We'll revisit each world briefly in a more meditative way, like repeating a theme in music. Then we'll close with a gentle goodnight and a soft invitation to like and subscribe if you want more of these quiet tours. So let's move into that slower closing rhythm now. Let's do a calm recap, not to test memory, but to let the images settle. First, the sideways orbit. A planet that seems to travel over the poles of 2 brown dwarfs. The system is dim, quiet, and yet its geometry feels bold. It reminds us that gravity does not care about our preferred planes. If the history of a system twists the disk, or if interactions torque an orbit, the result can be a world that moves in a direction we did not expect. Second, the baby planet in the ring. A disk with gaps, a small point of light nestled in a clearing. A world caught early, still shaping and being shaped by the material around it. If you imagine it slowly enough, it feels almost like watching a shoreline form. Not one wave, but millions of tiny motions. Dust and gas in gentle chaos. A planet slowly becoming distinct. Third, the dust tail planet. A rocky world so close to its star that its surface can vaporize. Material escapes. A tail forms. The planet becomes a source of its own debris. There is something fragile about that, and something useful. The tail is a clue. It is a sample. It is a brief chance to learn what rocky planets are made of when you cannot touch them. Fourth, the twin helium tails. A gas giant under intense heat. Its atmosphere puffs and expands. Helium escapes. Not in one neat stream, but in structures shaped by stellar wind and gravity. It is an exoplanet with a kind of invisible artistry around it, not painted, but sculpted by forces. Fifth,
the lava world that may still hold air, a small planet with a molten day side, a permanent day, a permanent night, and yet the possibility of a lasting atmosphere moving heat around the world. If this is confirmed, it suggests a resilience we did not fully appreciate. Even in extremes, there can be balance. Sixth, the pulsar planet with soot, a world in the neighborhood of a dead star's core, a place where we might not expect stable planets, and yet a planet appears, with an atmosphere that seems unusual, helium and carbon, soot-like hazes, and perhaps deeper layers where carbon can crystallize. It is a reminder that even after a star dies, systems can still contain complexity. Even in the aftermath, matter can organize. Now, here is a gentle thought that connects them. These worlds are strange because they show different answers to the same questions. How do planets form? How do planets move? How do planets change? How do planets hold on to gas? How do planets survive their stars? Our solar system offers one set of answers. The galaxy offers many. And the deeper truth is that planet is not a narrow category. It is a spectrum of outcomes under gravity and chemistry. If you want to keep listening without thinking too hard, you can treat each world as a texture. A tilted ribbon orbit, a glowing dot in a ring, a comet-like tail, two pale helium streamers, a molten hemisphere and a moving sky, a soot-darkened atmosphere under a strange star. Textures, not tests. Now, the episode title says of 2025, and that matters for one more reason. It means we are living in a moment where the pace of exoplanet discovery and characterization is accelerating. Not only the number of planets, but the number of planets with properties we can describe. Temperatures, atmospheres, chemistry, geometry, evolution. This is not a guarantee that every year will bring headlines, but it is a direction. As instruments improve, the galaxy will look less like a set of dots and more like a landscape. We will get better at direct imaging. We will get better at atmospheric retrievals. We will get better at mapping heat and winds. We will get better at distinguishing noise from signal, especially in the sensitive question of potential biosignatures. And the strange will multiply, not because nature becomes stranger, but because our perception becomes sharper. Now, a quiet question. If you could choose one instrument to improve next, what would you want it to do? Would you want a telescope that can image Earth-sized planets directly? Would you want a spectrograph that can map winds on rocky worlds? Would you want a survey that finds the nearest temperate planets around quiet stars? Whatever you choose, your answer reveals what kind of future you are hoping for. Now we're nearly done. In the last two files, we will return to the bedtime pacing, slower sentences, softer emphasis. We'll end with a gentle goodnight, and, if you're open to it, a subtle invitation to subscribe for more of these quiet cosmic documentaries. So let's go there now.
In the dark, when the world is quiet, it can help to remember how much is happening beyond our window. Not in a loud way, not in a way that demands attention, just in a steady, patient way. Stars form, disks swirl, planets condense, orbits settle, atmospheres grow, leak, and sometimes vanish. Systems evolve for billions of years, and we, on a small planet, build instruments that can sense some of it. A tiny dimming, a tiny wobble, a faint spectrum, a whisper of heat. It is enough to reveal a gallery of strange worlds. And perhaps the best way to hold that strangeness is not to turn it into spectacle. The best way is to let it make the universe feel larger, because a larger universe can be calming. It reminds you that your own worries are not the whole landscape. They are a local weather system inside a much wider sky. Now imagine the exoplanets again, but as if you were looking at them from very far away. You are not a tourist. You are not arriving. You are simply aware that they exist. A planet that orbits sideways, a planet that is being born, a planet that is dissolving, a planet that is leaking its sky, a planet that may still carry air in intense heat, a planet under a dead star with a strange chemistry. They exist whether or not we name them. They exist whether or not we understand them fully, and that is a quiet kind of beauty. Reality does not need our comprehension to be real, but it is also true that comprehension can deepen wonder, not the wonder of fantasy, the wonder of true complexity. Now, if you want a simple calming exercise, you can do this. Picture a star. Any star you like, not the sun, a star far away with a name you do not know. Now picture a planet around it, not necessarily Earth-like, just a planet. Now picture another star and another planet and another. As you repeat, the image becomes a pattern. The galaxy is full of stars, and stars are often accompanied by worlds. And if worlds are common, then strangeness is common too, because some fraction of worlds will live in unusual orbits. Some will be too hot, some will be too young, some will be too close, some will be under rare kinds of radiation, some will be in systems that were disturbed by companions. The galaxy is a statistical generator, and our solar system is one sample. That perspective is quietly comforting because it means that Earth is not a lonely exception. Earth is rare in its details, perhaps, but not in its existence. It also means that the pace of discovery is not a fleeting trend. It is a reflection of how many targets the sky is willing to offer. In 2025, the catalog of confirmed exoplanets crossed another major milestone, a reminder that we are no longer in the era of a few exotic finds. We are in the era of populations. Populations allow comparisons. They allow patterns. They allow us to see which kinds of worlds are common and which are rare. And they allow us to recognize that a strange world is often an extreme example of a broader class. A tail of dust is rare, but it tells us about surface loss. A helium outflow is not unique, but seeing its structure teaches us about escape. A lava world with an atmosphere is surprising, but it teaches us about survival under heat. A polar orbit is unusual, but it teaches us about the third dimension of system architecture. A
A baby planet in a disk gap is a snapshot, but it teaches us about the sculpting hand of gravity. In that sense, strange worlds are not distractions, they are boundary markers. They show us where our models begin to bend. And there is something gentle about models bending. It means the universe is not correcting us with harshness, it is guiding us with evidence. Now, we can end this episode with a final reflection. The strangest exoplanets of 2025 are not a statement that the universe is chaotic. They are a statement that the universe is flexible. Physics allows many outcomes. Nature uses them. And in the future, we will likely find worlds that feel even stranger. We will find planets that blur categories. We will find atmospheres we did not predict. We will find systems that challenge our formation models. And then, slowly, we will integrate them. We will update our understanding. We will build better models. The strange will become part of the map, and the map will become calmer, not because it loses mystery, but because it becomes more complete. If you are still awake and you want to engage one more time, which world from tonight's gallery stayed with you the most? Was it the baby planet in the ring? Was it the comet tail world shedding dust? Was it the twin helium ribbons of the ultra-hot Jupiter? Was it the lava world with possible air? Was it the sideways orbit around brown dwarfs? Was it the soot cloud planet near a pulsar? Tell me in the comments what image you carried away. I read them, and they help shape what we explore next.
Now, one more file remains. We'll close softly, and we'll place the call to action gently, without breaking the mood. As we close, let's return to the simplest thing we did tonight. We looked, we listened, we let distant worlds become quiet images. That is, in a way, what astronomy has always been: a careful attention to faint signals, a willingness to be patient, a calm acceptance that reality can be larger than intuition. In 2025, that attention brought us a few especially memorable scenes. A planet whose orbit seems to rise over the poles of two brown dwarfs. A newborn world glowing in the gap of a dusty ring. A rocky planet with a tail slowly shedding itself into space. A gas giant with helium streams, a double ribbon shaped by wind and gravity. A molten world that may still carry air, redistributing heat against expectation. A planet near a pulsar with a carbon and helium atmosphere and dark haze. If you take only one idea from this episode, let it be this: planet is not one picture, it is a family of outcomes. And every time our instruments improve, we see another branch of that family. We learn that worlds can form in warped disks. We learn that worlds can be born where we can finally see them carving a ring. We learn that worlds can lose themselves slowly, leaving traces behind. We learn that atmospheres can cling to bodies under extreme heat or stream away in ribbons. We learn that even in the aftermath of stellar death, matter can organize into something planet-like. This is the quiet power of science. It does not ask reality to become simple. It learns how to describe complexity without panic. Now, if you are listening in bed, you do not need to carry the details. You can let the names fade. Just keep the feeling, a wide sky filled with variations.
And if you want one last question to leave with you tonight, here it is. When you imagine the next decade of discovery, what do you hope we find? Not necessarily a perfect Earth, not necessarily proof of life. Maybe you hope we find a planet we can directly image with oceans and clouds. Maybe you hope we find a quiet, stable atmosphere around a small, rocky world. Maybe you hope we find a new class of planets we did not expect. Maybe you hope we learn how common or how rare certain conditions truly are. Whatever your answer is, it is a gentle kind of optimism, a belief that there is still more to know. Sometimes the most restful part of astronomy is not the answers, it is the scale. Scale makes space for breathing. It makes room for perspective. It reminds you that your life is real and important, but it is not trapped inside a tiny box. If sleep is difficult tonight, you can borrow one more quiet image. Imagine the Milky Way as a dim river of light. Along that river, imagine countless small lamps, stars. And around many of those lamps, imagine small companions, planets, some hot, some cold, some newborn, some ancient. You do not have to solve anything. You do not have to picture them sharply. Just let the idea exist. A galaxy full of worlds, each following gravity in its own way. And if your mind wants to wander, let it wander slowly. Let it drift from one world to another, the way a calm camera drifts through a quiet scene. One slow breath in, one slow breath out. And if a thought arrives, you can treat it the same way you treated the planets tonight, as something real but distant, passing gently through the sky of your attention. If you enjoyed this quiet tour and you'd like more episodes like it, calm, documentary, sleep-friendly explorations of space, you can support the channel in a simple way. You can like the video so it reaches more listeners who want a peaceful cosmic atmosphere at night. You can subscribe so you don't miss the next episode. And if you know someone who falls asleep best with gentle science stories, you can share it with them. No pressure, just a quiet invitation. In the next episodes, we'll continue the series with topics that connect to tonight's themes. How the cosmic web behaves like a living structure. How exoplanet atmospheres reshape our ideas of habitability. How new instruments change what we consider known. For now, you can let the images fade. Let the ring of dust dissolve into darkness. Let the tail drift away like a comet in slow motion. Let the helium ribbons become invisible again. Let the lava world cool in your imagination. Let the pulsar's clock-like pulse become a distant, steady beat. And let your own thoughts become quieter. Good night.